This module, we will talk about how to calculate the amount of land area that is needed to supply the all of the energy needs of the United States using only solar panels. So solar panels produce electricity, and using electricity, if we decide, we will power all of our needs, including transportation, industry, houses, heating and cooling in houses, and lighting, and all of those things. How much land we need if we use only solar panels. And you may be wondering how we do that for transportation. Well, it, basically, you'll have to use electric cars. Okay, so let us assume that we can supply all of our energy needs using electricity from solar panels. So how do we calculate that? So for this, I used some references. You can get a lot of information from the National Renewable Energy Lab website. They have maps. They have lot of tables, all kinds of data about how we use energy, how much we used last year, how much we will use next year, how much we expect to use in the coming years. I also used a very nice paper from MIT. A whole bunch of professors from MIT have put together this report called "The Future of Solar Energy," and it talks about what changes need to be done if we are to power a majority of our needs using solar panels. I encourage you to look at both of these resources, the NRL website and also the MIT paper, because they talk about, you'll find a lot of information there, very useful, interesting information that we will not be able to cover in this little video. Okay, so we are trying to calculate how much um, we land area we need to so that we can put enough solar panel to supply all of our energy needs. Now, first we need to figure out how much energy or how much power we need. What is the amount of power or energy that we are consuming? By the way, power is just the rate of energy. So if you consume certain amount of energy per second, then that is the power that you're using. That's just the physics definition. Okay. But for us, power and energy will mean pretty much the same thing. Anyway, so this map shows you how much energy we used starting from 1980, and they are also making projections all the way to 2040. And it shows, it's a very nice graph in the sense that not only they show how much we are using, but also how much of each type of fuel we are using. And so you have petroleum, you have coal, you have nuclear, you have biofuels, you have renewables that includes solar and wind, and you have natural gas. And these are used in different ways. Of course, we use petroleum for our cars and trucks. We use coal for electric power plants that supply our electricity. Of course, nuclear plants also supply electricity, and then solar and windmills, they supply electricity. Natural gas is mostly used for heating, both at homes and in factories. And natural gas is more and more being used to power electricity power plants instead of coal, because it's cheaper and cleaner. So this graph is from the Department of Energy website. There's a part of DOE that is called Energy Information Agency. That's what you see here, EIA, and they also are a good resource for various kinds of information about energy, all kinds of energy. And so it shows you that the total that were used in 2013 is 97. You can see here, this is the total, 97.1, and the unit is in quadrillion BTUs. I will explain what that is in a second. So this is the total amount that was used in 2013. As you can see, it's been increasing, and then it's not going up too much, and they are assuming that we will find better ways to use energy and waste less of it, so that our increase, even with population increasing, industry increasing, that the energy use won't increase that much. We can also see how they project various sources. They project that coal use will remain about the same, but natural gas will increase a little bit, and renewables like solar and wind will also increase a little bit. So you can look at this data, just this graph, and learn a lot of interesting insights. Okay, so that's the amount of power we need. Let's see exactly what that means, the quadrillion BTUs. So BTUs are British thermal units, and it's used, it's a way to measure energy, and it's used to measure the electricity, um, the energy from heating fuels. After all, it's called thermal units. That's so how much energy it takes to heat certain amount of water through 1 degree. That's really what it means. And the total energy consumed includes electricity for homes and industries, gasoline for transportation, and natural gas for heating, all of those things. And that was 97.1 quadrillion BTU in 2013. And 1 BTU is this much kilowatt hours. And kilowatt hours is what we normally use to measure energy, especially electric energy. And so suppose you use 1,000 watt, which is kind of the standard for our microwaves. Um, if it runs for 1 hour, then you use 1 kilowatt of energy, kilowatt hour of energy. Or you burn a 100 watt bulb for 10 hours, you also use 1 kilowatt of energy, kilowatt hour of energy. A better way to understand it is that 3 gallons of gasoline, and you can drive about 100 miles on 3 gallons on the average car. That also produces about 100 kilowatt of energy. And the same energy, 100 kilowatt hour, if you drive an electric car, can go 300 to 400 miles. So that's the total amount of power that we are using, except I didn't say what quadrillion is. I'll come to that in the next slide. Um, all right, so this is the actual next slide. The questions and assignments will come in the end. Um, this is how to calculate or convert the BTUs into kilowatt hours. So, as I promised, 1 quadrillion means 1,000 trillion, which is trillion is 1,000 billion, and you hear about it a lot when they talk about the government budget and stuff. Or the GDP of the US is about $14 trillion. Anyway, a quadrillion is 1,000 trillion, and that's like 10 to the 15. And so 97.1 quadrillion BTU equals 97.1 times 10 to the 15, and times that much in kilowatt hours. So if you multiply all of that, here we use a little bit of scientific notation. So if you move the decimal to 4 places to the right, then 10 to the 15, you reduce it to 10 to the 11. So if you remember from college algebra 1, that's how you convert to scientific notation. You have decimal, one digit before the decimal, so you have 2.93, times 10 to the 11. So this part becomes 2.93 times 10 to the 11, just to make it, more compact. You multiply all of that, you get 284.5 times 10 to the 11 kilowatt hour approximately. And that is the total amount of energy that we are using. So it's about 28,000 billion kilowatt hours. Um, and you can also write it in megawatt hours or gigawatt hours or terawatt hours. All of these are used in the industry. A megawatt is 1,000 kilowatt, a gigawatt is 1,000 megawatt, and a terawatt is 1,000 gigawatt. Anyway, for us right now, let's just look at this number here. It's 284.5 times 10 to the 11 kilowatt hours. That is the amount of energy that was used altogether in all kinds of ways for transportation, heating, industry, everything, electricity, natural gas, all of that produces energy, and all of that total comes to 284.5 times 10 to the 11 kilowatt hours approximately. So now the next question is, how much power can a solar panel of area 1 square meter produce? So if we can figure out how much power can come from one solar panel uh, with a 1 square meter area, then we can figure out how many solar panels or how much land area you need to supply 284.5 times 10 to the 11 kilowatt hours. So that's the total amount of power. So we can figure out how many solar panels or how much land we need to cover with solar panels in order to produce all of our energy needs. So one solar panel of area 1 square meter on the average is produces about 15 watts per day. This information is this is an estimate. This estimate is from the MIT study, future of solar, and they use all kinds of assumptions. So you have to account for the amount of sun's energy falling at a certain place, and how it can vary based on the season, the time of the day, and the angle, and all of that, and how it can be affected by cloud cover. And so various things go into the calculation of this number here, 15 watts per day, and that is from the MIT future of solar study. So that's on the average. So on the average, in a day, if you multiply by 24 hours, 360 watt hours, that is the amount of energy that can be produced by 1 square meter of solar panel. So that's 0.360 kilowatt hour. Remember that 1000 watts is 1 kilowatt, and if you multiply by 365, you get 131.4 kilowatt hours per year. And just for reference, 1 square meter is about 11 square feet, 10.76 more precisely. All right, so we now know how much power we can produce using 1 square meter of solar panels, and we also know what is the total amount of power or energy that is needed per year. So this is from the NRL, the Renewable Energy Lab website. This amount. This is from the MIT paper, and so if you divide this amount by this amount, you get the amount of land that you need, or amount of square meters that you need to cover by solar panels in order to supply all of our power needs. Remember, all of our power needs includes the electricity for homes, the natural gas for homes, of course assuming that instead of natural gas you use electricity to heat it, and also, so basically you replace all of the energy that comes from all kinds of fuels right now. That's petroleum, natural gas, nuclear. You replace all of that with electricity from solar panels. So you drive electric cars instead of gas powered cars. So you make all kinds of changes. So assuming you can do that, that you supply everything using solar panels, then how much land we need? We need 216,500 square kilometers. So 1 kilometer is 1,000 meters. So 1 square kilometer is 10 to the 6 or 1 million square meters. So after converting this number to square kilometers, you get this much. And that's about 83,000 square miles. And it's about 2% of the land of the US. Just to give you an idea of how much is 215,600 square kilometers or 83,000 square miles. This is the land area that we need. So this amount here, that's the land area we'll need to cover up using solar panels entirely in order to produce. So if you cover all of this area, and you see it's not that big, it's just over 2% of the all of the land area, and there is a lot of empty space, like in the deserts and places like that. So if we can just cover that by solar panels, then we can supply all of our energy needs, including transportation, heating, cooling, all of that. Finally, do we really need that much land? Even 2%, that does look like a lot of land, but fact is that's just just playing with numbers. You don't really need that much land. A lot of the solar panels are going to be on rooftops of homes or buildings or warehouses, like Walmart and IKEA have put up a lot of solar panels on their roof. Many other companies are doing the same. So you don't really need new land in order to put solar panels. So that way you can reduce the amount of land you need. And also, if you remember the 15 watts per square meter, that was based on a lot of assumptions. So that was the average. If you put it in an area like Arizona or Nevada, where there is above average sun energy, solar energy coming in, and also you use more efficient solar panels, which will definitely be there in the future, then you can reduce it much further. You really need only 1/3 of the area that I showed you in the previous graph, and you can read more about it in the MIT paper. You got to go there and look in Appendix A, that has the calculation. In fact, what they calculate is how much land is to produce electricity alone. If you look in that paper, they also do a similar calculation. They come up with a smaller land area. That's because they are looking at electricity alone. They are not looking at heating and cooling and transportation and all of that. And you can other possible questions or assignments that may be asked is how much land or ocean area. Some wind turbines are these days are being put in the ocean. In the Europe, they have a lot of that near Denmark, especially. So you can also use wind turbines to make a calculation of how much area you need to cover with wind turbines to supply all of our energy. And you can also see how much farmland you need. A lot of ethanol, a lot of farmland has been converted to producing corn for ethanol, and so lot the if you have noticed in some petrol stations, they have 5% ethanol or flex fuel as they call it. So so the government has mandated that some amount of ethanol can be mixed with petroleum to produce gasoline. So you can also produce electricity using ethanol. So it'll be interesting to see how much farmland you'll need in order to produce all of our electricity using ethanol alone. So those are some questions, and if you go to the website on Blackboard or on my website, course website, you can see more information, more assignments, or um, websites where you can go and get more information. So that's all for now.